be negative 4x, and in the denominator, a negative quantity getting squared becomes positive. Now, if in this case, if you observe the end result here, we get the same function, all right? However, notice how in this case we got the opposite in sign. In this case, we got negative f of x, which means the function is odd or symmetric about the origin. All right, that is, if you rotate the function 180 degrees, the graph of the function, not the function, the graph of the function rather, you should get the exact same picture in your Cartesian plane. All right, so well, that's pretty useful information when it comes to sketch the graph of the function in the end. Now, determine the end behavior of each interval. That is, well, in this case, we need to plot on a number line all the values of x corresponding to vertical asymptotes and intercepts. From there, we're going to evaluate the function at some test values to determine the signs of the y values, which ultimately will tell us whether the function will approach, or the graph of the function will approach the horizontal asymptote from below or from above. And we determine that based on comparing the value of the horizontal asymptote versus the output of those test points. Well, again, my advice, put open bubbles for for vertical asymptotes, and solid bubbles for intercept, and then turn this into a number line. Notice I drew two open bubbles, that for -2, +2, which are the corresponding vertical asymptotes, and the x-intercept, which is at 0. So our test values would be any number in each interval. Notice in this case we have, first of all, let me turn this into arrows. All right, and keep it easy when it comes to getting the test values. I mean, you can choose -50 million if you want, but keep it easy. Keep it the number closer to it, -3, -1, 1, and 3. All right? Well, so let's test these points and plug them in the original function. F of -3, that's again, replace -3 wherever you see the letter x in your original function. That is 4 times -3 over -3 quantity squared minus 4. That is -12 over -12 over, that's 9 minus 4. That's -12 over 5. All right? And we would do the same thing for the other test point. I'm just going to write the results to it. I mean, taking the whole lecture to plugging values, I think you know how this works, right? I'm just going to do one for every single exercise. So f of -1, that'll result into 4/3. F of 1 equals to -4/3. And f of 3 equals to 12/5. Now, notice something interesting here with the values that we obtained. So, as you can tell, look at the y values. The y values repeat, except that they repeat with the opposite sign. And that's because of the symmetry that we have about the origin. We have the exact same locations, but in the opposite side, on the opposite side with respect to the origin. This is the kind of behavior we get with functions that are odd, or functions that, or graphs of functions that are symmetric about the origin. Now, well, we will need this, and I think let's just sketch the function with all the information that we have. So again, well, if you use colors, make sure to draw the asymptotes using red. That's usually, you know, the kind of red flags for those values that the function is not supposed to touch, you know. And what do we get in this case? Well, so we have We have two vertical asymptotes. Number one at -2, one at +2. We have a horizontal asymptote, y equals 0, which happens to be the x-axis itself. All right? And any x-intercepts, well, x-intercepts, that's the origin, which also happens to be the y-intercept. And also it happened that it happened to be a point where the function crosses its own horizontal asymptote. So let's plot the points, the additional points, to get an idea of what we should get. All right, so we plotted the point -3. So -3, and we got -12/5, which happens to be roughly here. All right. Then we got the point -1 4/3. So -1 +4/3. That's a little over 1. This point, and then the point 1 comma -4/3, and another point we got over here, the point 3 comma 12/5, which is roughly here, right? So this is the graph that we are going to obtain, something like this. Notice how the graph crosses its own horizontal asymptote, and also has this limits going from below, because again, if in this case, for example, for x equals -3, we got -12/5. That should be below 0, below the horizontal asymptote. If we otherwise would have obtained a positive value, it would have approached from the top in this case, right? And of course, you can always use a graphing calculator to check your results. But again, recall what we talked about graphing calculators last week. Graphing calculators don't ever show asymptotes, don't ever show those holes, which are usually called removable discontinuity. So we need to be very careful with graphing calculators. So it's important to keep in mind what you know about the theory of the functions and all that, and put it together with the graphing calculator. All right, that being said, let's look at another example. Let's see. So the graph of 2x² - 3x - 5 divided by x² + 1. All right. So number one, let's get the intercept. To get the y-intercept, all we do is plug in x equals to 0 to simplify for y. That's going to give us the order pair corresponding to the y-intercept. In other words, f of 0, 2 times 0 squared minus 3 times 0 minus 5, divided by 0 squared plus 1. That's going to give us, 0 in the numerator, minus 5, that's a -5 over +1. That's a -5, which gives us the order pair 0, -5. And let's see what's next. Okay, finding the x-intercept. So notice for the y-intercept, we made the x equals to 0. In the y-intercept, in the x-intercept, we're going to make the y equal to 0 instead. So that is, set the function 2x² - 3x - 5 over x² + 1, set it equal to 0, multiply both sides by the denominator to simplify the equation, to turn that rational equation into a polynomial equation rather. And well, notice how things cancel over here. That's going to lead us to the equation 2x² - 3x - 5. And while this is a polynomial equation, recall that there's a bunch of ways to solve this equation by factoring, completing the square. That's going to take forever. Looking at the coefficients, that takes forever. Quadratic formula, that's going to take some work as well. So factoring would be better in this case. And recall I showed you a few different ways to factor this type of polynomial, where the leading coefficient, in this case the coefficient of the quadratic term, is different than 1. So use the method that you feel more comfortable with, guess and check, or the diamond method, whatever method you feel better with. So I'm just going to give you the result for this. That means x equals to 5 halves and x equals to -1. So we have two vertical asymptotes, one at a rational, well, 5 halves, and the other one at -1. So we're starting to get some of the important information for this function. Any vertical asymptotes? Well, notice for vertical asymptotes, observe the leading terms of each numerator and denominator. And one thing to observe over here is that both have the same degree. That is, the degree of the numerator matches the one in the denominator. So in this situation, all we do is y equals an over b sub m, and just identify the numbers 2 over 1. That equals 2. So we have a horizontal asymptote of the form y equals to 2. All right, let's see what's next. The next part to determine whether f has horizontal or slant. Wait a minute. No, that was supposed to be a vertical asymptote. That one goes here. And vertical asymptotes. Oh, for vertical asymptotes, all we do, focus on the denominator. X squared plus 1 equals to 0. But check what's going to happen here. X squared equals to -1, and then x equals plus or minus the square root of -1, and that's plus or minus in the imaginary unit in this case. Well, we don't want imaginary numbers in this class, only real numbers, so this means no vertical asymptotes. All right, no vertical asymptotes in this situation. Well, let's see what's okay. The horizontal asymptote, we already got it. And now we will determine whether f crosses its own horizontal asymptotes. And well, all we do is set the original function. Let me write it down. 2x squared minus 3x minus 5, and divided by x squared plus 1, and set it equal to the value of the horizontal asymptote, that equals to 2. And yes, initially this equation is going to look a little scary, but you'll see what's going to happen here. So let's multiply both sides by x squared plus 1 to turn this rational equation into a polynomial equation that we can solve it a lot more easily. That's going to lead us to 2x squared minus 3x minus 5 equals to 2x squared plus 2. And the good thing, again, check this out. Check how the square terms get canceled, because they show on both sides, which is going to be great, because in the end we will have to deal only with a linear equation and not a quadratic equation. So that equals to 2, and then negative 3x equals to negative 7, or actually positive 7, and x equals 7, negative 7 over 3. So that's the value of x where the graph will cross its own horizontal asymptote. Testing for symmetry, let's see, what about it? Again, get the original function, replace every instance of x with negative x, and well, all we do is simply replace, and then minus 3 times the negative x minus 5 over negative x quantity squared plus 1. Well, let's see what we're going to get here. So these two terms squared, when we square a negative, it goes back to positive. That's a 2x squared, and here plus 3x minus 5 over x squared plus 1. And in this case, let's look at this function. The result we got over here doesn't match neither the opposite or of the original function nor the same function. So all it changes actually, so let's go back. That's positive, negative, negative, and positives in the denominator. The only thing that changed was this positive. So we needed everything to be opposite in sign to call this given function an odd function. That is a function whose graph would be symmetric about the origin. Or otherwise, if we've had obtained the same original function, it would have been an even function. That is a function whose graph is symmetric about the y-axis. So in this case, no symmetry, or neither. Neither symmetry. All right. And we'll end behavior, draw a number line, test values. You know the drill for this. So let's see. So we have two vertical asymptotes. Those are going to go with open bubbles. However, how many inters? Wait, we have. Oh, no vertical asymptotes this time. Only two x-intercepts, by the way. All right. So two x-intercepts. Then I'm going to draw with solid bubbles, and that's it. This time we didn't get any vertical discontinuities, any vertical asymptotes rather. And well, those intercepts again. When we draw this number line, we need to plot the numbers in ascending order, from smaller to larger, to have a number sense. Of course, a number sense in this. In the sense of increasing, you know. So that's going to be -1 and 5 halves. That's what we got for this x-intercept, and let's get the test values. So -2. What else? -2. I think they got -2, 0. And well, 5/2 is the same as saying 2.5, so the next easy number to test would be the number 3. So let's see what about it. So f of -2, which happens to be function, so 2 times, let me go back, okay, 2 times -2 times 2 times -2 squared, plus, or rather -3 times -2, and then -5, and then divide this by -2 squared plus 1. Simplifying the numerator, we should get 2 squared, that's a 4 times 2, that's 8, and minus, that's a plus 6, and -5. The denominator, that's a 4 plus 1, and that's 14 minus 5, I think that's a 9/5. And yeah, that's a value I got over here. All right. And of course, let's do the same for the other two test values. I have space in the next page here. So that's f of 0 and f of 3. So f of 0, I got -5. And f of 3, I got 2/5, 2/5. So again, plug in the value, simplify the usual, you know how this works. So with all this information, these extra points, this, the horizontal asymptote that we got, the point where the graph crosses its own horizontal asymptote, and the fact that we don't have any vertical asymptotes, well, that's good enough to sketch the graph for this function, which is the next part. All right, so let's see. So let's sketch the function. So number one, we got some intercepts. Let's see what we got for the intercept. We got a y-intercept at 0, -5. That's going to be this point over here. And what else did we get? We got two x-intercepts. 5 halves, which is 2.5. That's roughly here. And -1, 0. Then we got we got a horizontal asymptote at y equals to 2. So at y equals to 2, we're going to draw a dashed line. Recall that horizontal asymptotes are represented with dashed lines. Both, well, actually all kinds of asymptotes, horizontal, vertical, slant, or even polynomial asymptotes. Well, we're going to discuss one example that includes, what's it called? Slant asymptote in the next example, I believe it. Yes, I believe it's the next one. What else did we get? Well, no vertical asymptotes. The denominator didn't have any real solutions when we set it equal to 0. What else? Let's see. The point where the graph crosses its own horizontal asymptote. That is, the point negative 7/3. Negative 7/3 is roughly 7/3 is a little higher than 2, I guess. So 8/4 is 2, right? So it's actually a little higher than 2 because 6/3 it's 2, so it's going to be roughly here, all right? Okay, however, check this out. It looks like we already plotted everything. We already plotted everything from the information. However, we need one additional point. So we need an extra point to determine whether the graph of the function will do this or that. And for this, we will need to plot another point. Say, okay, let me go one more. How about -3? I'm gonna plot the point -3, f of -3, and when we plug in that value, we get 11/5, which is a number a little higher than 2, since the number, well, 2.2. Let's say 2.2. I'm gonna estimate 2.2. Well, the idea for this is to tell whether the graph is going to approach the horizontal asymptote. Is it going to approach it from above or from below? Well, in this case, it's going to approach it from below because that point, -3 and 11/5, is going to be this point. So in this case, when sketching the graph, this point is going to work like a minimum, and it's going to do this, all right, roughly. Well, about that minimum and maximum, well, that's something, how to get those maximums and minimums, well, that's something you will be able to do next semester when you take Calculus 1. So when you get to applications of the derivative, which is a pretty cool operation to help us determine the maximum or a minimum, and also has a bunch of applications to optimization, which is stuff that it's done, in the industry when you have a business, you're selling whatever you sell and you want to find a way to maximize your revenue or to maximize your profit. So that's what calculus is going to be for. Or you want to know what's the values for the minimum loss. You don't want to lose money, right? That's part of the business here. Okay, so how about we look at this on the graphing calculator. So I would like to look at the previous example as well. So what did we get? 4x over x squared plus, or rather minus 4. Okay, so where's my, here it is. Open my graphing calculator and get the function y equals to, let me clear, that's 4x divided, oh, careful, when when typing rational functions on the graphing calculator, make sure to use parentheses correctly, because this is I'm going to do it the incorrect way, just to show you what happens when you do that. So x squared minus 4, and Let me graph this. So that's the graph I get when I type that function, and clearly that doesn't match the graph that we got over here. In fact, if you look at the graph on the graphing calculator emulator here, is missing one of the vertical asymptotes in this case. And from the algebra that we did for this third example or so, there's one asymptote missing. So what's the issue here? Well, so it turns out that the denominator here, because the denominator involves an addition or subtraction of multiple terms, make sure to put parentheses around. Open parentheses and close them at the very end. Notice I didn't do those parentheses in the numerator because the numerator is only one term. But if the numerator happens to have more than one term, then make sure to enclose both numerator and denominator as its own group of parentheses. I'm going to show you how that's going to work on the next example. So in the meantime, let's look at the graph for this one. And check this out. Does that match a lot better with the graph that we did by hand? Yep. Much better? And let's see. Well, do you want to draw the horizontal asymptote? There's a little trick. So the horizontal asymptote, which is y equals to 0 over here. And then over here you have additional ways to, so like this, like that, like shading inequality. No, we don't want to do that. And that's the dashed line. And let's graph. No, it didn't work. Actually, there's another way to do it. Oh, I don't think I did hit the OK. Oh yes, I needed to hit the OK. I wanted red, and I need to click OK. And for some reason, I need to maybe zoom in. And it sort of looks dashed. For whatever reason, it doesn't look dashed all over. I don't know why anyway. But that's a good trick to draw horizontal asymptotes. For vertical lines, it's a longer trick. You have to like get into the programming section of the graphing calculator. It's a little tedious, but again, as long as yes.
So on tests, will we be able to use a graphing calculator?
I don't think so. That's a good question. I will confirm. I will talk to the coordinator about it, and I will give you an answer for that next time. That's a good question. Thank you. And okay, let me go back to the original Zoom. That's number 6, the standard, -10 to 10. All right. And let's look at the graph for the other function that we just plotted: 2x squared minus 3x minus 5. And where is it? It's right here. All right. So notice, first of all, notice how I will open parentheses for the numerator, because this time the numerator contains more than one term. It actually contains 3 terms. So 2x squared minus 3x and minus 5. And then open parentheses as soon as you're done typing all terms in the numerator. Again, missing these parentheses is going to lead to the incorrect graphing. Now I'll show you after I'm done. So divide by, and the denominator has 2 terms, open parentheses, that's x squared plus 1. All right, and graph. It sort of looks like the graph that we drew by hand, right? Let's have a look. Sort of. So let's have a look at the horizontal asymptote. So the horizontal asymptote, what was that? Y equals to 2. Just so you can see the asymptotic behavior on the graphing calculator. So y equals to 2 and graph. All right. Do you see how the graph, in this case, crosses its own horizontal asymptote kind of reaches a maximum value and then starts approaching the horizontal asymptote from above, but actually never touching it. It's going to go all the way to negative infinity, but without ever touching it, all right? Okay, so the pitfalls here, again, let me, because I'm pretty sure this is stuff that happens all the time. Let me delete the parentheses. It's very easy to forget about those parentheses. So, and well, good thing it's on record on the video, so when you watch it again, that reminds you of not doing this at all right? So, let's see, delete. Oh, should have cleared everything. Anyway, 2x squared minus 3x minus 5 divided by x squared. All right, so that's the function without the parentheses. Check what we're going to get. Not even an asymptote at all, if you notice. No asymptotes at all. Whoa, wait, actually there's an asymptote, I think. Because, nope, not second, just, and yeah, negative 5 over x squared, so kind of a horizontal asymptote somewhere, kind of a weird thing, but otherwise it's just a polynomial. It's just a polynomial function, essentially. Nothing, it doesn't have anything to do with this graph at all. All right? So, all right, so let's see. Let's look at one more example. Let's get started with it. So notice, well, it looks somewhat similar to what we did before. That's a quadratic polynomial in the numerator. That's a linear polynomial in the denominator. And well, I think by just eyeballing the function, we can sort of tell what is this going to look like. Well, the denominator definitely, it's already showing some discontinuity, some value for which the function it's going to be undefined. That is, well, we'll find out algebraically, but by just looking at the function, that's going to be, what's that? Negative 3. But the numerator, that's another polynomial that will require some algebraic steps to get those intercepts. And let's see. Determine the y-intercept. So first things first. F of 0, 2 times 0 squared plus 9 times 0 plus 4 over 0 plus 3. And well, pretty much everything zeroes out except this 4 and the 3. That means 0 4/3 is going to be our y-intercept. All right, getting the x-intercepts. For this, we set the whole function set it equal to 0 and solve the equation. Multiply both sides by the denominator x plus 3, and notice how this cancel. That's going to lead us to, I'm going to go over here, 2x squared plus 9x plus 4. Set that equal to 0. And again, we have a polynomial equation, a quadratic equation, for which we have a bunch of ways to solve. Quadratic formula, factoring, completing the square, but I'm just going to do the factoring. That's 2x and x. And the result for this, that's going to be 2x plus 1 and x plus 4. You can do the foiling to verify that, and that you will find out that it's going to take us back to the original polynomial. So, using the zero product property, that means 2x equals to negative 1 and x equals to negative 1/2, and otherwise x equals to negative 4. So we get 2x intercepts. All right? 2x intercepts, and let's identify any vertical asymptotes. And well, let's recall that in order to get vertical asymptotes, all we do is set the denominator equal to 0, because that's what indicates the values for which the function is undefined. Again, functions that will lead a 0 in the denominator. So x plus 3, equals to 0. That means x equals to -3. It's a vertical asymptote in this case. And again, before we move on, let me go back to the previous part, to part B. Notice I just gave you the x values for where the function crosses the x-axis rather, but we should write this as order pairs, in fact, not just x values. All right. Horizontal, slant asymptote, or none of them? Well, so let's observe the graph of the function. Let's observe the form of the function. In this case, again, polynomial over polynomial, but we happen to have the situation in which the degree in the numerator is higher than the degree in the denominator. All right. So in this case, what do we have? A sub n to be greater than b sub n, and differ by 1 unit. That means in this case we are going to have a slant asymptote if the degrees in this case differ by 2 units or 3 units. Well, it's neither horizontal nor slant. In fact, we will have asymptotes that look like a parabola. It's actually a parabola in a dash way, or even weird polynomials in dash form. Well, there's a lot of weird things, and in this case, all we have to do is perform the polynomial long division. That is 2x squared plus 9x plus 4, and in this case divide by, well, let's write down the divisor, which is x plus 3. So we need to do this polynomial long division to figure out what the slant asymptote is. That is, it's going to be a diagonal line. Well, just to check this with the operation that we are about to do. So notice, we are dividing a second degree polynomial by a first degree polynomial. If we think at the overall degrees of these two polynomials, degree 2 over degree 1, so all we do essentially is divide a square over a linear. So the overall result will be, or the end result will be, something that is going to be degree 1. And degree 1 indeed matches the shape of a linear function, of a diagonal function. So it's important to check this kind of ideas, to check for consistency with what we're doing. All right, so that being said, let's divide leading term of the divisor by leading term of the dividend. So 2x squared over x, that's going to give us 2x. And I'm going to write it down on top of the x's to have everything organized by powers. You can write it everything, whatever. You can write it whatever you want, but my advice, just write it on top of its corresponding power. So 2x. So 2x times x, that's going to be 2x squared. But again, positive times positive, it's positive. But by the principle of the division, we get the remainder by subtracting, which essentially changes the sign of what we get. And 2x times 3, that's a 6x. But subtract, change the sign. Cancel these two. Cancel these two. And 9x minus 6x, that's a 3x. And then 3x. So that's the new leading term. In this case, first of all, drop the next term. That's the independent term. And every time, so the way the division algorithm works is that we need to check that the first remainder that we get. If the degree of the first remainder that we get, it's still higher or the same than that in the divisor, then we still need to do another iteration of the division. So in this case, I'm going to divide 3x by x. That's going to be a 3 3 times x, that's a 3x, but change the sign. 3 times 3, that's a 9. And but change the sign, that's when simplifying this, these two cancel, these 3x's cancel, and 4 minus 9, that's a negative 5. But ultimately, we are not going to care about the remainder. All we care about in this case is just the quotient. And the quotient over here, which is 2x plus 3, isn't that a linear function? Isn't that a linear form? Well, that's what we were checking for consistency before doing the polynomial long division. And in fact, this will indeed reflect into getting a shape that looks diagonal, that is the slant asymptote, right? So slant asymptote, that's going to be y equals 2x plus 3. And it's going to be dashed. Because again, that's how we draw the asymptotes over here. All right.